mass-energy relationship. Einstein proposed that mass and energy are equivalent, which means that if the mass of a body is converted into energy, the energy released will be delta E equal to delta M times C squared, where delta M is the loss in mass, or we say delta M is called mass defects with unit in kilogram. Delta E will be the amount of energy released in the unit of joule, and C is the speed of light in vacuum, which is equal to 3 times 10 to the power 8 meter per second. Example 1. The mass of an apple is 100 grams. Find the energy released when all its mass is converted to energy. By Einstein's mass-energy relationship, the energy released delta E will be equal to delta M C squared, which is equal to 0.1 kilogram times 3 times 10 to the power 8 and the square, which is equal to 9 times 10 to the power 15 joules. We see that only a mass defect of 100 grams will produce a huge amount of energy. Atomic mass unit a.m.u, or we say U, is the unit of mass in atomic scale. A. What is meant by 1 a.m.u or 1 U? By definition, 1 U or 1 atomic mass unit is equal to 1 over 12 times the mass of 1 carbon-12 atom. B. How to find 1 U? First, we see mass of 1 mole of carbon-12 atoms is 12 grams, and 1 mole of carbon-12 has 6.02 times 10 to the power 23 atoms. Therefore, mass of 1 carbon-12 atom will be equal to 12 grams over 6.02 times 10 to the power 23. Therefore, 1 atomic mass unit, 1 a.m.u or 1 U, equal to 1 over 12 times 12 grams over 6.02 times 10 to the power 23, which is equal to 1.67 times 10 to the power negative 27 kilogram. Example 2. The atomic mass unit of a proton and a hydrogen-2 nucleus are 1.007276 U and 2.013553 U respectively. Find the mass of a proton and a hydrogen-2 nucleus in the units of kg. Since 1 a.m.u or 1 U equal to 1.67 times 10 to the power negative 27 kilogram, therefore we have mass of a proton will be equal to 1.007276 times 1.67 times 10 to the power negative 27 kilogram, and the mass of a hydrogen-2 nucleus is equal to 2.013553 times 1.67 times 10 to the power negative 27 kilogram. C. What is meant by 1 electron volt, 1 eV? 1 electron volt, 1 eV is the kinetic energy gained by an electron when it is accelerated by voltage of 1 volt. D. How to express 1 electron volt, 1 eV in terms of joules? By definition, 1 electron volt equal to 1 eV equal to 1.6 times 10 to the power negative 19 coulomb times 1 volt, which is equal to 1.6 times 10 to the power negative 19 joule. It must be looked at both electron volt, eV, and joules are units of energy. Part E. When a mass of 1 U is converted to energy, what are the amount of energy released in units of joules and megaeV? By Einstein's mass-energy relationship, delta E equal to delta M times C squared. We have the energy release delta E equal to the mass defect for 1 U is equal to 1.67 times 10 to the power negative 27 kilogram, and times C squared, which is 3 times 10 to the power 8, and the square of it, meter per second, and the square of it, and the energy release will be equal to 1.503 times 10 to the power negative 10 joules. When changed the units of energies from joules into eV, electron volt, the energy release will be equal to 1.503 times 10 to the power negative 10 over 1.6 times 10 to the power negative 19 eV. 9.39 times 10 to the power 8 eV, or equal to 939 megaeV, because 1 megaeV equal to 10 to the power 6 eV. Notice that a mass defect of 1 U is equivalent to an energy release of about 939 megaeV. This conversion is very important. Example 3. The mass of a helium-4 nucleus is 4.001506 U. Find the energy that the mass equivalents in units of megaeV and joules. Since a mass defect of 1 U is equivalent to an energy release of about 939 megaeV. Therefore, for the helium-4 nucleus, its mass is 4.001506 U, which is equivalent to an energy release of 939 times 4.001506 MeV, and is equivalent to an energy released in the units of joules, which is 939 times 4.6001506 times 1.6 times 10 to the power negative 19 times 10 to the power 6 joules. Example 4. If a uranium-235 nucleus is completely converted to energy, the amount of energy released is 6.28 times 10 to the power 28 MeV. Find the mass of uranium-235 nucleus in U. Since an energy released of 939 MeV is equivalent to a mass decrease of 1 U. Hence, the energy release of 6.28 times 10 to the power 28 MeV will be equivalent to a mass decrease of 6.28 times 10 to the power 28 MeV over 939 MeV in the units of U, which is equivalent to 6.69 times 10 to the power 25 U. Hence, the mass of a uranium-235 nucleus is equal to 6.69 times 10 to the power 25 U. Energy released in nuclear reaction. A. Why energy is released during nuclear fission and nuclear fusion. In nuclear fission and nuclear fusion process, the total mass of the particle before reaction is larger than the total mass of the particle after the reaction, and the mass defects or the mass loss is converted to energy, which is shared by the products as kinetic energy and heat. B. Let's see what is the energy released in a nuclear fission of one uranium-235 nucleus. For the nuclear fission process shown, we have mass of 1 neutron, mass of 1 uranium-235 nucleus, mass of 1 barium nucleus, and 1 of mass electron nucleus are given. The mass loss during fission is the initial mass Mi minus the final mass Mf, which is equal to mass of a neutron plus mass of uranium mass minus mass of barium mass of electron and mass of 2 neutron, which is equal to 0.192789 U. Hence, the energy released during the fission process will be 0.192789 times 939 mega-eV, which is equal to 1.81 times 10 to the power 2 mega-eV. Part C. Let's see what is the energy released in a nuclear fission of 1 gram of uranium-235 nuclei. We see that mass of 1 mole of uranium-235 nucleus is about 235 grams, and the Avogadro number is the number of atoms per mole, which is 6.02 times 10 to the power 23. Therefore, 1 gram of uranium-235 nuclei will have 1/235 times 6.02 times 10 to the power 23 number of uranium-235 nuclei. Therefore, the amount of energy released by 1 gram of uranium-235 during nuclear fission will be equal to 1/235 times 6.02 times 10 to the power 23 times 1.81 times 10 to the power 2 mega-eV. D. Now let's see what is the energy released in nuclear fusion between one hydrogen-2 nucleus and one hydrogen-3 nucleus. From the equation of the fusion process, we have mass of hydrogen-3, mass of hydrogen-2, mass of helium, and mass of neutrons are given. In this case, the mass lost during the fusion process is the initial mass minus the final mass, which is Mi minus Mf, which is equal to mass of helium-3 plus mass of helium-2 minus the sum of mass of helium and the mass of a neutron, which is equal to 0.0188882 U. Therefore, the energy released in the nuclear fusions between one H2 nucleus and one H3 nucleus, delta E, will be equal to 0.0188882 times 939 mega-eV, which is equal to 17.7 mega-eV. Part E. Let's see what is the energy released in a nuclear fusion of 1 mole of hydrogen-2 nuclei and 1 mole of hydrogen-3 nuclei. Avogadro numbers equal to the number of atoms per mole, which is 6.02 times 10 to the power 23. Therefore, the amount of energy released by 1 mole of H2 and 1 mole of H3 during nuclear fusion is 6.02 times 10 to the power 23 times 17.7 mega-eV. F. Will there be any energy released in a radioactive decay process? Similar to nuclear fission and nuclear fusion process, radioactive decays result in a decrease in the mass. That is, the mass of the parent nucleus is larger than the total mass of the daughter nucleus and the mass of the radiation produced. In this case, by Einstein's mass-energy relationship, in radioactive decays, energy is also released and can be found by using the equation delta E equal to delta M times C squared again. Example 5. Radon 222 nucleus decays to polonium-21X nucleus by emitting an alpha particle, and in this case 5.59 MeV of energy is released. Given the mass of radon 222 nucleus and polonium-21X nucleus are 222.017577 U and 218.008970 U respectively, and you're given 1 U is equivalent to 931 MeV. Write down the decay equations, and the decay equation is this one. Part B, find the mass of an alpha particle. We see that delta mass is equivalent to delta E, and a change of mass of 1 U is equivalent to a change of energy of 931 MeV. Now, the energy released is equal to 5.59 MeV. Then, what is the mass decrease? Obviously, the mass decrease equal to 5.59 over 931 U, and mass decrease delta M will be equal to mass of a radon nucleus minus the sum of mass of a polonium nucleus and the mass of an alpha particle. By substituting the mass of radon equal to 222.017577 U and the mass of one polonium nucleus equal to 218.008970 U, and equate delta M equal to 5.59 over 931 U, we can find the value of the mass of one alpha particle. Now let's go to a conclusion for nuclear fission, nuclear fusion, and radioactive decay. Is there any mass loss? There is mass loss in nuclear fission, nuclear fusion, and radioactive decay. Is there energy released? Of course, since there is mass loss in these three processes, therefore there is energy released in these three processes. Are these processes spontaneous processes? We see that radioactive decay process is a spontaneous process, which is uncontrolled by physical change. However, nuclear fission and nuclear fusion processes are not spontaneous processes. Then, what are the necessary conditions for this process to be proceed? For nuclear fission process, there must be slow neutrons. For nuclear fusion process, there must be a high temperature. However, for radioactive decay process, since it is a spontaneous process, therefore there is no necessary conditions.